Okay, ladies and gentlemen, welcome to this Google Hangout on the theme of big science. My name is Olivier Dessibourg. I'm the head of the Science and Environment section at the daily newspaper Le Temps in Geneva. So we're here to talk about big science, and before starting, before giving the word to our two speakers, it may be good to think back on what is actually big science, where did it come from? So one has to step back just after the Second World War, a period during which Europe was experiencing some really major changes on the industrial level as well as scientific field, following just the Manhattan Project with the atomic bomb. At the time, international agencies decided to construct and develop major scientific infrastructures like CERN, for example, or the Apollo program. At the time as well, a guy named Alvin Weinberg, he was the director of the Oak Ridge National Laboratory. He wrote an article in the journal Science, and although he would actually recognize the good old times of little science, he described the paradigma change that is big science in those words, and I'll read them to you. Throughout history, societies have expressed their aspirations in large-scale, monumental enterprises which, though not necessary for the survival of the societies, have taxed them to their physical and intellectual limits. History, often viewed as monuments, he quotes the pyramids, the cathedrals, Versailles, as symbolizing the societies. When history looks at the 20th century, she will see science and technology as its theme. She will find in the monument of big science symbols of our time. So when we talk about those symbols, we can have, for example, as mentioned, the program Apollo, the CERN, Fermi, and the SSC, which wasn't constructed at the end, the Human Genome Project, the International Space Station, for example, ITER, the fusion reactor, the LHC, of course, the future FCC, being built at CERN or anywhere else in the world. The Human Brain Project we'll talk about, astronomy with the upcoming EELT, the Extremely Large Telescope. For example, these are examples. So many possibilities, we have to make choices, we cannot build all of them. And actually, Weinberg also said, big science is here to stay, but we have to make the hard financial and educational choices it imposes. So make choices, but based on which criteria, with which goals. That's what we'd like to talk about today with our two speakers. And there are Hans Peter Beck. He's high energy physicist at Bern University. After studies made at Zurich University in physics, maths, and astronomy, he worked for a while at the DZ Synchrotron in Hamburg before coming to Bern. He's now a spokesman for the Swiss Institute of Particle Physics. As a high-energy physicist, he regularly uses, since 1997, the research infrastructures provided at CERN. Of course, amongst other now, the LHC. He particularly worked within the ATLAS team, one of the big four experiments that are disposed around the LHC. So as a member of ATLAS, he's amongst the thousands of scientists that managed in July 2012 to discover the now famous, very famous Higgs boson. 6,000 amongst one of them is Hans Peter Beck, but as his name is Beck, he must certainly be on the top of the list, which is a good thing. And please, Hans Peter, take 2 or 3 minutes to talk about the project you worked on.
Okay, thank you, Olivier, for this nice introduction. Yes, indeed, we are running very big projects, and having my name on top of the list, well, in hydrogen physics it's not important because we list alphabetically and not via contribution. And B with B, and if there are 3,000 names for Atlas, you don't manage to be top on the list. You would have to have a name starting with a triple A. Okay, so regarding hydrogen physics, and to introduce big science, I would like to start with a quote from Mr. Wilson, who was a founder of Fermilab near Chicago in the USA. And of course, he needed a lot of money to build Fermilab, and he had to go to the American Congress and bid there for the money. And the Congress, of course, asked, well, will this new lab be useful to defend our nation? Defense always in the heart of the politicians. And the answer of Wilson was very clever. He said, no, but having this lab, it will make worth the nation to be defended. So this is in the spirit of what I try to do, trying to push humanity, to push human curiosity forward, and having these, we're speaking of monuments like cathedrals and pyramids and other big things being done in the past. I think today it's indeed the way how we bring in together nations in big multinational global projects to build something which makes humanity worthwhile and being a light pole that historians in the future will come back to us. Now to CERN. CERN is built in, have been founded in 1954, is now 60 years old. We just had big celebration for the 60 years birthday. There are about 10,000 physicists these days working at CERN from all continents over the whole globe. Basically, every nation almost is somehow participating to CERN. Not every nation is member of CERN, but physicists from all over the place come to CERN and use the infrastructure. The LHC itself, the Large Hadron Collider, is a very big project. It's a 27-kilometer circumference underground tunnel at 100 meters below France and Switzerland in the Geneva region. We're colliding protons at unprecedented energies. And out of these collisions, we try to learn how nature works. We try to learn what are the fundamental principles that govern matter and the basic constituents of matter. How do they interact? How do they work? And one of the results that came out that was big and famous was the Higgs discovery after a long search, and that you just mentioned. You always need at least 2 experiments when you come up with something new. So the Atlas experiment is one of 2 experiments that found the Higgs boson. The sister experiment is the CMS, the compact muon solid experiment, also at the LHC, but at the opposite side, 180 degrees on the other side, having been analyzing independent proton-proton collisions and came to the same conclusion: the Higgs exists. So we are sure that we do good science.
Thank you very much, Hans Peter. And our second speaker today is Richard Frackowiak. Richard is a professor and director of the Department of Clinical Neurosciences at the University of Lausanne and also at the CHU, which is the university hospital in Lausanne. After his medical studies at Cambridge, his career brought him to the universities of Liège and University College London and at the École Normale Supérieure de Paris. He's a member of various academies of medical sciences, the English one, the French one, and the Belgian one. He was a president of the British Neuroscience Association and the European Brain and Behavior Society. But finally, what he's really interested in is try to understand the structure of the brain and its functional relationships with health, respectively illnesses. That's actually what led him to take the co-direction of the Human Brain Project, the huge European initiative with a budget of 1 billion euros, which he will now present in very few words because time is running fast. Richard?
Thank you very much, Olivier. So here we go. So what are the big challenges we have now in Europe? Well, essentially one very big challenge is what's happening to our aging population. It's aging because of the successes of medicine and science in the past, but as it ages, it's being subjected to a number of very difficult diseases, mainly ones that make people lose their minds. They're called the dementias sometimes. And we don't know what causes them, we don't know how to treat them, but they have enormous impact on society because they are people who are very quickly need to be helped, supported to the end of their lives. So how do we go about doing this? Well, the pharmaceutical industry has tried for about 15 years and failed. It's pulling out. A classical paradigm of science, of hypothesis-led science, has also failed. It's concentrated on topics which have not led very far. So one of the ways in which we can change this paradigm is to go about science differently, to start looking around outside our discipline and saying, well, who and what can help us? We've got lots and lots of data over 40, 50 years, lots of information about individual bits of neuroscience. Where we fail is to put it all together into some holistic whole, some blueprint of the brain, if you like, where new information can be put and understood. And the big thing that's happened in the last 15, 20 years, I think no one will contradict this, is the resurgence, a massive resurgence of computing and informatics. So what we've set out to do is to put informatics together with neuroscience in three ways. Firstly, through trying to build this blueprint, some people call this a model, to simulate the brain, to understand the principles of organization at all the levels, from genes right up to brain cognition, emotion, and the rest. The second is called future medicine, which is where we will try to use informatics to do big data analysis of all the data that sits locked up in our hospital research and pharmaceutical company databases, to try and redefine diseases in terms of what causes them, what's their biological basis, rather than just symptoms and syndromes. And the third is future computing, because it's the computers, the supercomputers, and the massive databases that are going to make this possible. And at the same time, our computing colleagues want to make computers which are more advanced than the traditional von Neumann digital binary computers, to take them into neuromorphic computing inspired by the brain. So that's the aim. This is the big science that Olivier talked about right at the beginning. We think that this is something which is appropriate for a big continent such as Europe, with all its traditions in science and computing and being at the origin of brain mapping and so on, could have an enormous impact on the whole world.
Thank you very much, thank you very much, Richard. So we have now actually a big half hour to discuss about this, and I will ask the audience, because we have an audience, we don't see the three of us, but we have a big audience, I presume, to ask questions using the group chat, the Google group chat, and I will relay the questions to our two speakers, Richard and Hans Peter. So please do not hesitate to ask your questions, writing them. Maybe my first question, and you may have partly answered it already, but is it actually really a necessity to have such big infrastructures to actually do what you want to do? Maybe Richard.
Oh, well, I think our change of paradigm demands that. You see, what informatics and computer power, calculation power give us is the ability to do something that the mind of a single person or of even of a research group cannot grasp. We currently have 3 million papers on neuroscience published and stored. We have, I don't know how many hospitals in Europe, let alone the world, containing masses of data, day by day accruing. These things are not treatable by the brain. They need classification, they need filing, they need reorganizing, they need to be confronted with each other, to be correlated with each other, in order to find these groups of patients who have the same problems in terms of what is wrong with their brain, rather than what is the manifestation of what's gone wrong in their brain. So we need an enormous infrastructure, there's no doubt about that. It will be transformative. It will transform medicine. It will transform the way we deal with private data and how we can use private data to advance knowledge without compromising that privacy. It will cause new industries to build up. That the algorithms and the apps needed to go and look for data in the databases around the world, and to bring the information together in a way which can be then analyzed statistically and so on. All these things are going to require big infrastructures. And I suspect Hans Peter would say something very similar.
Hans Peter, I'm sure in physics it must be a necessity, right?
No, in physics, of course, we are driven by fundamental basic questions that we would like to answer. And then we've tried to find tools and methods to attack these questions in an experimental, empirical way. And we know that big is, we are not convinced that big is beautiful, but we are convinced that we want to have our questions being answered, our experiments built. So we try to be as small as possible. But as small as possible still means very big devices. So we are not proud that LHC tunnel is 27 kilometers, etc., etc. But it's basically driven by the complexity and of the question we're trying to answer in order to advance science, in order to advance knowledge. We're trying to squeeze out the maximum of science with the minimum size infrastructure. But minimum size infrastructure still means quite huge or extremely huge. But we're not driven by making it big. We're driven by what is the best way and the still affordable, manageable tools in order to get to advance in science. While we do that, of course, we are faced with appearingly unsurmountable technical problems. It's too big, it cannot manage, it cannot work that. So we have then to break down and find ways how to build a very complex, very complicated, very big machine and have that up and running. And even that is a big process, driven by the needs that we have in order to push science ahead.
So one can understand that you actually built the LHC, amongst others, to look for the Higgs boson. So you actually built the very big machine that is the LHC with a very precise goal. One very precise goal, at least, was to find the Higgs boson. Whereas for the Human Brain Project, a critique that has been made is that you make this huge project, but the roadmap is maybe less clear because you first want to aggregate a lot of data, but then you have to make those data speak, actually, or tell us something, and you don't know exactly what they will tell us. Do you agree with that critique, Richard?
Well, I think it's a perfectly reasonable comment. I mean, science where you knew what you were going to find, well, there are sciences like that are a bit boring when they get to that stage. What you're always trying to do in science is to advance knowledge. Hans Peter put it very succinctly. To advance knowledge, you need to tackle problems which at the moment are unsolved. The roadmap, I would say, is extremely precise. That criticism I wouldn't take. We know what we have to do. We've analyzed all that. The question is, as we go forwards doing it, will we find what we expect? I hope not, because I hope that the reality is beyond our current imagination. But I hope that it will stimulate our imaginations then to go forward in new and more productive ways, and that the change in the way we do things brings about a whole new way of generating knowledge. One of the very basic things our roadmap demands is that people no longer sit in their offices or their labs doing their science and competing with the next person down the corridor. It means that we open ourselves up to collaborative science, not necessarily competitive, where a medic like me can go and see a head of a computer science department here at the EPFL and have a conversation which gives us new things to do and new ways of doing them. Perhaps not new things to do, the things that we want to do together, but new ways of doing them. So I think that, you know, as most criticism goes, it has truth in it, but it also has potential in it. And I think the potential of the Human Brain Project is exactly that it will be disruptive. It will change things. It will go beyond the way we look at things at the moment, and therefore it will generate knowledge. I don't know in history of a really big, well-developed, it took us 4 years to develop this project, which hasn't succeeded in generating advantages for society or advantages in terms of knowledge accretion. But perhaps you do, or perhaps Hans Peter does. But
No, actually, Richard, you offered me the perfect link to my next question, and then we'll go to the to a question from the audience. But the link to my next question would be, and you just said that maybe big science experiments are like big bangs in Switzerland now. They are called too big to fail, which means that in any case, scientists, after 10 years, having put $1 billion or more into the project, 1,000 scientists will find something to say or interesting things to say. So would you agree with the idea that with such big projects, science is too big to fail, which means we will certainly find something to tell the people at the end?
Well, I would agree, but nuance your conclusion. I mean, in a sense, my professional career, I've come up a big frustration. Well, a big frustration now. I've worked in medicine, working with symptoms and syndromes. I can't go any further. So if I spend more money doing what I'm doing now, I am failing, and big money is being spent on medicine at the moment. So big science can fail, just in the same way as big banks can fail. I think the real issue is whether you're spending big money on more of the same, or whether you're really pushing forward with a completely new paradigm and a new set of ideas. And that's the critical difference. And so the beginnings of such projects are very important. They have to be very, very well prepared. They have to be given time to get going. They will undoubtedly change their course one way or another, so there have to be mechanisms whereby they can adapt to what is found. But they are very big projects. They demand very big management. They're like big banks, if you like, in that sense. But we're all hoping in Europe that the big banks are going to give us some stimulus to our economy very soon, and that we're going to be able to go beyond the current apparently morose situation within which we find ourselves. So I will put a positive spin on it whilst agreeing with your analogy.
Hans Peter, what is your answer to that?
Too big to fail. What means fail? The LHC program, I take it as example, it could have been the outcome, there is no Higgs. The Higgs doesn't exist. Then people would have said, you failed. You promised with this machine we'll find the Higgs, and you would have concluded the Higgs doesn't exist. This is not a failure in the scientific sense. It has advanced knowledge. It would have told us that the theories we have, the ideas about the world we had, were wrong-footed. The Higgs does not exist in nature, so we were, and this would have been a strong correction in our views how physics works. This would have been a very big leap in advancing science. Also, you could see it has failed. It didn't produce the expected result. So when you do science, you don't know what will be the outcome. Only after you've done the experiment, you know the result. This is one way of what could have been perceived as a failure, but it would have been a wrong perception. But there could have been a real failure in a way that we would not have been able to manage LHC to run at all. Or we would not have managed to organize ourselves in a proper way that we can manage this very complex infrastructure from a technological side, from a finance resources side, from a human side. So this would have been a big failure and would be a big drawback in the type of research we're trying to push.
Yeah.
Certainly, this could mean the end of our field, and we all know that. So in that sense, yes, too big to fail, because when we fail, our field of research, our basic interest, and all our beliefs and dreams that we put into it would have the potential to come to a cease.
Okay, we'll go to the question from the audience, and the first one is both the projects at CERN and the HVP, which is based in Lausanne at EPFL, are based in the French-speaking part of Switzerland. So why do the researchers in the German part of Switzerland are less successful in acquiring such big science projects? Is there a reason for that? Hans Peter, you work in both in Geneva and Bern, so maybe you have both views of the question.
No, but for CERN, of course, the decision that CERN is placed in Geneva, this goes back to the time of end of World War II and rebuilding Europe. And Switzerland has been decided as a neutral place, so neutrality played a big role in deciding that CERN should be built near Geneva, around Geneva, and not the language, I think. Why CERN went to tend to the Geneva region was that because the United Nations were already established with the Völkerbund. I don't know the English term for Völkerbund. Has been there as a predecessor of the United Nations and then been turned into the United Nations. So all this international infrastructure and airport, etc., this was important for CERN to be decided to be in Geneva.
Richard, there was a project in Zurich in competition with the HVP for the choice of the two big European projects. Do you see any reason why, the French-speaking project, may I call it that way, in Lausanne was chosen instead of the Zurich one?
Well, I think the answer to this question is that science is now international. And actually English is its language. It used to be German, in fact, before certainly before the First World War, and certainly between the wars, quite largely as well. Why these things happen? Well, we live in cultural and political contexts, and so they happen. Where they're coordinated is another matter. Some university has to roll the dice. Perhaps currently the Suisse romande is rolling the dice more easily and more quickly than the Swiss alémanique. But we have quite a number of Swiss researchers in our consortia, including the German side, German-speaking side, I mean. We have a scientific leadership which is based currently in Lausanne, but also in Heidelberg. And next year I will be moving to Paris, so it'll be Lausanne, Heidelberg, and Paris. So I think these things just depend on things which are extraneous from us. The other thing to understand is the world is becoming much more connected. Look at what we're doing now. I mean, I'm sure the people who started setting up CERN had none of these facilities. So to do big science is much easier since we've been able to communicate in very much easier ways. So I'm someone who's a big believer in anti-nationalism. I think it's killed too many people in Europe over the last century and a half. I'm very much in favor of regionalism, where you can control something about your life where you live. And I'm a very big supporter of the European Union. So I'm really happy the way this has worked out. And I would say to our research, to our questioner, don't worry about this. Just coordinate, collaborate, send your ideas in. Why we won and the Zurich project didn't? Those are technical questions which the reviewers can only answer. I think, of course, our project's the best, but then I wouldn't I?
So let's talk about money now for a few minutes. A critique that is made, and we heard it this summer from regarding the Human Brain Project, is that if there is too much money put into just one big project, much less money is available for smaller projects and smaller groups. So do you agree with that critique? Is that something that you can understand, Richard?
Well, I think there are two answers to this question, and they both relate to the fact that we really are, one of our ambitions, and we're not at all sort of modest about this, is to effect a cultural change in our science. So in respect to the Human Brain Project, we went out looking for extra money. So that the money, which is about 7 billion euros per year, which is spent on neuroscience in the world, and the 1 billion spent in Europe per annum, is still there. And I, for one, have a research portfolio where I continue to compete for grants using my ideas as my competitive edge. And I believe that most scientists in this, if there is a transition phase to a new paradigm of collaborative science and interdisciplinary science, tackling the problems of the brain, I'm sure will continue.
But the theory...
That's one answer. The other answer, of course, is that if the ideas no longer command the money, then perhaps this is the right thing to do. But I wouldn't be so bold as to suggest that's correct at this stage. But all I'm saying is that we convinced people who work in informatics and computer science that the brain is a very serious and interesting for them object of study. And for that, I am very grateful, and for that, probably most neuroscientists are very grateful.
Yeah. Hans Peter, maybe there is another question coming from the audience, and it goes like this. What kind of particle accelerator will be the successor of the LHC? And the follow-up question could be, will all the money that will be invested in this future accelerator, so first, what is it? And then will it prevent smaller groups of physics to live, actually?
I think I would like first to answer the questions about whether big projects are trying out other fields, other areas. And it cannot come just like that. I want to build the next big machine after the LHC, and this will cost so and so many billion euros or dollars or whatever currency you need. It doesn't work like that. You do have to have a solid project with that they prove that you have a solid scientific goal that is considered as worthwhile pursuing by the community. You have to have a technical plan that you can convincingly prove that you can build the experiment, all the machines, the toolings, etc. You need to do that. You have to convince that you can bring up the people, etc. So you have to have a lot of preparatory work, which will take you many years to do before you can come and say, we have all at hand that we now want green light to start building the next machine or a big machine. Until you are there, you have reached consensus within the scientific community that this is what you're proposing is the right next step. And many small teams everywhere in the world, they're open to contribute. Because we are big science, not because we have one big funding agency that gives us all the money. We are successful because we have many small teams. A professor in a university with his postdoc, with his PhD student joins in and brings his normal resources. This professor could also decide, I build my own small experiment. As we have always done in the past, we had small experiments in our labs at the university, we do this and that, and we do science, we write a paper. That's fine. And this will continue. But you will not advance the very big questions that do need big projects. So it's not one against the other. It's how in some areas we cluster the resources, and in other areas the resources stay as they are. But I don't think that the integrated resources would be different. And I even question whether if there are too many professors who try to do the same thing, non-coordinated, independently, that they would all do basically the same or very similar things. We wouldn't advance because it's not needed that we have 100 times the same projects or the small project, even if it's a tiny bit different. We have to be science driven and find the big answers and find the tools to answer those, and then cluster the resources.
In few words, the future accelerator?
For the future accelerator, this is also scientifically driven. There are big groups, big teams thinking about how the next machine should look like from a technological perspective. And it could be a linear collider, it could be a circular collider, it could be an electron-positron machine, it could be a proton-proton machine. All options are open on the table, and for all options there are teams working. Which one we will concentrate on will be decided also with the outcome of the results out of the LHC. The LHC has now been in shutdown for 2 years almost, and will resume taking data doing science starting in spring 2015. if it comes out that because we will have almost twice the energy, with twice the energy, we can explore a new frontier in where we haven't studied our physics model. So in there could be new sensations to lurch on. If you find anything there, we don't know, we cannot say for sure, but we are looking, then this would change the attitude, what will be the next important steps. If you don't find anything there, then the Higgs stays in the center. And this will be very decisive of what should be then the next steps for the next big machine. And the next big machine will only be built if we are convinced it's scientifically solid and needed, and is the best thing we want after wavering all options on the market, building up big collaborations, teams that are, yes, we want to contribute, and convincing funding agencies and public that this is a worthwhile goal to do.
So let's dig actually this aspect. At the time in the 60s, the big science projects were mainly about hard science, physics, right? Big physics projects. And now the life sciences projects come in, like, for example, the human brain projects. We had the human genome project like 10 years ago. But the money pie, the pie stays basically the same. The governments don't have much more money. So what are the criteria actually to choose which project money should be given to? Some say one criteria should be the usefulness to society. Would you agree with that? What are the criteria to decide on to which project to give money to? Richard? Yeah.
These are decisions that are made at a political level, if you like. In other words, they're decisions which are made after a lot of consultation with the scientific community, but also with the taxpayer. I mean, you know, I pay my taxes. I want to know what they're going to be spent on. And it's then the business of the people who put up the projects or put up the ideas or who want to influence the way things that will go to present a case which is convincing. The brain has been at the center of the public's interests for 20 to 30 years. You need pick up only popular journals. There are frequently pictures of functioning brains, images of brains this, brains that. What the complete reason is for this fascination is, of course, probably would be the study of a PhD sociology thesis. But certainly, as we have moved from the heart as the center of the definition of our individuality, so now the brain is the center, and people are fascinated by that organ. Now, in the discussion that leads to these big decisions, clearly a politician needs to know that the money is going to multiply. All the evidence is that money invented in the life and health sciences over the last 20 years has multiplied by anything from 80 to 180 times. And that return on investment has been assessed, for example, by the Wellcome Trust, but also by big American consultancies, to be continuous. So there are strong political reasons, strong as manifesting the will of the people, what interests them. There's strong social reasons, because people are worried about their health and what will happen in the future. All of us have been touched at least once by either a demented or a psychiatrically ill relative or friend, and know what that means. And then finally,
I think we've lost Richard.
Yeah. So maybe before giving the word to you, Hans Peter, I would like to remind the audience that it's maybe the last chance to ask you questions before this hangout will end. So Hans Peter, can you actually compete with it? It's fascinating what Richard told us about the brain and so on. When we talk about axions, fermions, and so on, so-called particles, can we compete in terms of in public interest?
I think what is matter? What is matter made out of? Which then has direct implications of how is the universe constructed? How does the universe work? These are very old, very deep questions to humanity. And, this link is properly established, so cosmology doesn't work without particle physics. In a sense, if you want to understand what happened at the Big Bang, how did everything come up from? I think there's a very deep interest by the public in what we're doing, if we come from this angle and with this respect. Also, the microcosm has always been fascinating. So I don't think it's...
I'm back. I'm sorry. I seem to have had a connectivity problem.
Yeah.
I've returned.
Okay. So I do think that what we are doing is fascinating, and our deep question, if getting answers to deep questions from humanity over the history of humanity. Then we're also not just taking the money we get and burning it. We're creating something new with that money. We're building big machines. We're advancing knowledge. We're driving technologies, we're driving materials, we're driving all kind of sciences. We create spin-offs, and these spin-offs, they pay back. So think about how the world would look like without basic research in physics. The world would not look, we would still be farmers somewhere in the fields and pulling a plow with an ox. So
maybe
it
a
really has...
follow-up question, Hans Peter, just a follow-up question from the audience. It said, more than new particles, what's next for the LHC? Which means, what kind of other fields are you exploring actually with the LHC?
Okay. No, the LHC indeed has not just been built for the Higgs alone. This would have been a too narrow scope. The LHC is an exploratory machine which will still run about to the mid-2030s, 2035, if we can convince CERN and the agency and government that we need, that is to pursue the program that long, because that costs also money. Not just building it, but also running it costs money. Our aim is to go up to the up to 2035 about. This is when we scientifically have worn out the LHC. And we have deep questions about what is dark matter? What is dark energy? What is the difference between matter and antimatter? Why is in the universe matter dominant and antimatter practically not existing? So these are deep questions that we try to answer. Why is gravity so much weaker than all the other than electromagnetic forces is a deep question. Why is the proton, which is built up of quarks, has it exactly the same opposite charge as an electron, which is a lepton? And basically, where is this symmetry coming from? What is the base of that? So we do have a lot of deep questions that we are attacking with the LHC, and this will take more time. And of course, the Higgs physics being pursued in parallel.
Yeah. So maybe a question now from the audience that concerns both of you, because it's not your field at all from both of you. And the question is, will nanotechnology have a say when it comes to funding? So another field, a new field coming in, grabbing a part of the pie, will it have a say?
Well, of course, it'll have a say if they say. You know, nanotechnology, of course, is a broad term, and it could relate to aspects of computing, and certainly relates to aspects of treatment of disease, with various nanoparticles and so on being used already to deliver drugs, to act as contrast agents in brain imaging and such like. But if nanotechnology wishes to tackle a particular problem and to find sufficient funding, then it needs to convince the population, then it needs to make sure the population convinces its politicians, and then those politicians must find the money. That's a job which takes time. It takes 5-10 years. It takes a substantial piece of preliminary data and experimentation. It demands that the people pushing those ideas can mobilize their colleagues in sufficient numbers to create a critical mass, to generate a big program, and to get going. Personally, I have no qualms about nanotechnology. I think it's absolutely fascinating, already making a big impact, and will continue to be funded. Whether it goes for a big project like this, it depends on nanotechnologists.
Maybe the last questions before this hangout ends, and this will be a more maybe philosophical one. It seems like, you know, to tackle those big questions, those really profound questions about knowledge and all we need to know, or we would like to know, we need bigger and bigger and bigger machines all the time. Will this quest actually sometimes end? Maybe Hans Peter?
I think humans are curious creatures on this planet. They will always find questions to attack. The drive of these questions may change. That's possible. But we will continue being curious, and we will have the questions that we want to answer, that we think are important to answer, those we will attack. Whether this will be with new big accelerator machines, I don't know. I don't have a crystal ball to look into the future, but as long as we are humans, we will be curious and try to answer more questions on this planet.
Yeah, I mean, I would certainly echo that. In the 20th century, technology has driven science. Methods have driven science, and that's just a fact. Whether that will be so in the future, I don't know. I could easily conceive of science being driven in the direction of how can we find out things with lesser and lesser amounts of data? How can we find the principles which mean that the data are no longer as important because we can figure out in a prospective manner, in a predictive manner, what is going to happen given a new set of data which comes along which needs explanation. So I wouldn't be categorical about yes, it'll come to an end, or no, it'll always be technology. But certainly technology and technological methods is what have driven the inquisitive spirit along certain lines into certain directions, and which is presumably why the physics and material sciences have really flowered much earlier than the biological and the life sciences and neuroscience, which are taking advantage of all the advances made by the physicists now, really 100 years after modern physics was born.
But maybe a very last and follow-up question is this one. Curiosity is actually the characteristic of individuals, whereas on those big science projects you have like thousands of people working together. So would you say big science and big science projects actually fuel human curiosity?
I think we are driven by answering a big question. We build up a community and they think, yes, finding the Higgs is important. We will spend a large fraction of our life on that question in a huge big community. But this is not that everybody in this community does every day long the same. If you break down that project into all its aspects, you have so many smaller projects that each by itself is extremely difficult to tackle. So your curiosity is satisfied in many belongings, many aspects while you go along building up that project, setting it up, running machine, doing the analysis, thinking about the next steps, going to the future. So this is every individual finds its place where it contributes best and becomes vital for the success of the project. Of course, there is one big question in the end, but there's so many steps in between. I think we are not. Everybody has to be creative, ingenious, and bring in his best aspects together.
Yeah, I think this is just a part of the way we work. I mean, you know, in the Middle Ages, it was how many angels dance on the head of a pin, but that brought around the whole Renaissance and all the questions and problems of the soul in the individual, liberty, equality, fraternity, etc., etc. So the aim of a big science project is a vision. You get lots of things happening. I mean, the example that always comes to my mind is actually a physics example. They went off looking for the structure of matter and the theories about which needed Higgs bosons and wonderful things which none of us understand. But they actually gave us the protocol which allows us to do what we're doing today. the World Wide Web without the Internet protocols would have not existed. So, there was a lot of invention and a lot of things going on, despite the fact that people were really going along one roadmap towards one vision.
Thank you, Richard. I think this will be the final words. I thank you, Hans Peter Beck, as well. Thank you, Richard Frackowiak, for this hangout. We wish you successful researches in both of your fields, and wish you good luck. Thank you very much.
Thank you very much indeed. Thank you.
Goodbye. Thank you.
Bye.